that looks better. Okay. Today we're going to take a few notes. Make sure you have your notes out in front of you. I was going to do a Nearpod today, but we only have 20 minutes, and I don't want to waste 10 of it just trying to get set up and logged in. Maybe later next week we'll kind of go to the Nearpod thing again. Goal today is to intro the next section. I said I wanted to do that today. Just intro. We have a couple of properties here today, but they're based on the stuff we've already previously discussed. So don't think of it as like things that are radically new. It's not. Obviously, you can see the topics we're talking about. We're talking about arcs, which is the thing that was in your homework, right? The actual curves on a curved body. And then the chord itself in a circle, like the line that cuts through a circle and hits a circle twice. Okay? Where the endpoints are actually on the circle. So these are the two topics. The goal today is to show how they're related. Because the idea of a chord, they don't really talk about it a lot in like junior high and elementary days. They just don't. They talk about radii and diameter and circumference and area. But they really never talk about the importance of a chord and what it can do. So that's kind of the goal today, is to talk about those first two properties. So I have kind of a rough goal what I want to get to today, and this is going to be quick. It goes pretty easy. Goals. We have a couple of properties today that I want to talk about. I don't think or feel that we're going to get to probably all of them. Just kind of keep that in mind. So whatever we get to today. I'll just kind of go through these kind of slowly. Just make sure you understand what they're saying. Again, they're about arcs and chords. And then homework was due today. Just keep that in mind. That was your page 710. That was the stuff that I assigned last, this past Tuesday. And just note on that problem, because we modified the homework. It was like only the last 4 or 5. You had to figure out you had to use this idea that the Ferris wheel had a radius of 24 feet, because then you had to find the distance along that Ferris wheel. So, because I think the book said you had to find a central angle, right, on that Ferris wheel. So, it had, A and B, and I think the question in the book said like a number 26 or something. I'm just making this up. It said like, find the measure of AB. Like, that's all it said. Like, that's what it wanted. But I also wanted you to go one step further and actually find the distance you traveled on the actual like Ferris wheel itself from A to B. So you had to use that. You had to use the angle that they gave you, because maybe for some reason you could figure it out. Maybe it turned out to be, 42 degrees. Let's say. I have no idea. I just made up that one. So let's say it was 42. And then what you could do is, using this radius, you could figure out how far you traveled. Because this M meant the 42. Like, that's what they wanted. That's what they wanted, like, as the book problems, number 26. But what you have to do is go one step further and use this formula, which is taking the radius times your angle, and that gives you how far you traveled on an actual Ferris wheel. So the radius in our case is 24 feet. We're going to take that times my angle, but we had to make sure we had to do that little conversion, because you couldn't just use degrees. You weren't going to use the 42 here. You have to change it. You have to change it to what they call radian measure. It's just a different form of measurement for angle. So you take 42 times pi divided by 180, and that converts the angle we're using. That was the central angle, this thing. It converts it to radians, which is something we use for defining arcs on a circle. Questions on what you have to do on those last few. The other ones were very straightforward. Figure out a central angle or what the measure of an arc is. It was just a lot of angle stuff. Those last ones, I want you to figure out the actual distance you're traveling. Okay, any other questions on that before I move on? Perfect. All right, let's get to the new stuff today. All right. So let's get to our first theorem here, which is relating an arc to a chord. So here you go, 10.2. It's our second theorem, I guess, of chapter 10. The first theorem we had, that was Monday and Tuesday, we talked about that. In a circle, two arcs are in a circle, in the same circle or congruent circles, two arcs are congruent if and only if their central angles are the same. Well, this one talks about if two minor arcs are equal, then their corresponding chords are equal. So now we're not just talking about arcs and central angles, now we're talking about an arc and a chord. And I'll explain once I'll let you write this down first. But again, this is the second theorem. It's now relating your arcs to an actual chord, not just central angles. Again, if you ever want to know, it's on page 715. So some people like to know what, page in the book they're found and whatnot. So I'd like to know that. Page 715. If you ever had to look it up. Alright, so same circle or congruent circle. So we could have two different circles going on here, but they have to be congruent circles. What we talked about last Tuesday and on Monday this week, we talked about what makes circles equal is that they have the same radius. That's one of the definitions. They have the same radius. Or if they're within the same circle, then no problem. It only has one radius length. But we're talking about two minor arcs are equal if their corresponding chords are congruent. So here we go. So this is the picture they were talking about. So we're, on this example, I just used one circle. I didn't show two. So we have one circle. What we're going to try to show is if, and this is an if and only if statement, so it's a biconditional. Biconditional is when they use the word if and only if. That's the idea. So we're going to start with the fact that the two arcs are the same. So this arc is equal to that arc, like the actual distance. And what we're going to try to show is that these chords are the same. That's what they call a corresponding chord. It's an idea that it touches the endpoints of the arc that it was making. So that's what we're going to try to prove, that FG, the actual stick, is equal to JH, that stick. Now, I'm going to show you a different picture here in a minute, but that's what we're trying to show. Okay, questions at all about this problem? Now the next picture I'm going to show, because I have a second picture, explains how can we even remotely start that? How do you even know that you can do that? And that comes down to knowing that last previous theorem that we had, that if two arcs are equal, if and only if their central measures are the same. And that was that first theorem that we talked about. Okay, but everyone had enough time to write it down? Sounds good. Nelson, you good? Okay. All right, perfect. So let me show you the second picture. This is the picture I want to use. Okay. This is how we do it. So I know I switched up the letters, but what they start with the fact is that we use radii in the actual circle. So I just pulled this picture from the book because I really liked it. So the goal is I'm starting with the fact that two arcs are the same. Okay. And what I'm going to try to show is that QR is equal to ST, the actual stick. But we're given that arcs are the same. So I'll put this over here. So we're given that, line one, if we're doing a full-on proof, I'm not going to do this, but if we're given the proof, we're given that QR, the actual arc, is congruent to ST, that arc. The actual distances are the same. That was a given. What I need to get to in the end is eventually, down the road, QR, the stick, so a bar above it, the actual segment is equal or congruent to ST, that stick. That's what I'm trying to show in the very, very end, whatever step that is. I have no idea what number that is. But this is the picture, why it works. So I'm gonna, we'll kind of walk through this and then we'll talk about how do you know. So the first fact, that's why they stated this first sentence, you have to have a bunch of radii for this picture. So what do you know about radii of a circle? What do you know about these four sticks here, here, here?
They're equal.
Yeah, they're all the same, right? Because it doesn't matter where you move a radius, it's still the same length. It's like the best way I can always explain to people is like a hand on a clock. It doesn't matter where you put it, it's still the same hand. It didn't magically grow, unless you have a weird clock. But they're the same length. So I'm going to make a little mark there. So all these radii, that's what, QP, RP, PT, and PS, those are all the same stick. And then the last thing was knowing that previous theorem that we talked about. That was theorem 10.1. We did it earlier. I talked about congruent arcs. But arcs are equal if and only if their central angles are the same. Well, the central angle, so since these arcs are equal, using that previous theorem, 10.1, since these arcs are the same, that forces these central angles to be the same. That's a central angle. That's how arcs are worked, like the measure of an arc. And the reason why I know that that has to work, that those angles have to be the same, is because of that formula I just showed you a little bit ago about the Ferris wheel. That if you have an angle and a radius, that proves that you can go along a circular path the same distance. So when you're looking at this, now what I'm trying to prove is if I can prove that these two triangles are equal, then yeah, the sticks that are the chords, you know, Q, R, and S, T, those would also have to be equal. Well, what acronym does it spell? When you,
SAS.
yeah, it spells SAS, because we have that little acronym system back in chapter 4 and chapter 10, or chapter 4 and chapter 8, I should say, about triangles. These were the options we had, right? That you could prove that certain triangles are equal because of these, and these last ones were because of right triangle. So this is not a right triangle; it didn't have to be. But you're absolutely right. It has to be by SAS. When you actually look at it, side, angle, side, and that actually proves that the two triangles are equal. And then if the triangles are equal, then duh, the last stick has to be the same. QR, ST have to be the same stick. So that's actually the definitive proof of like why these things work. But it's using that last previous theorem that we did, 10.1. That was the one I think we talked about Monday or Tuesday this week. Arcs are the same because the central angles are the same. So that was kind of a crucial part. But the weird part about this theorem is that it didn't matter if we went the other direction, because it's an if and only if statement. It's a biconditional statement. So we could have started with the fact that the chords are equal, prove that arcs are. So if I was going to start with a different style proof, where maybe the chord here is the same, not the arc. Let's get rid of these arc markers. Prove that the arcs are the same. Well, it is that I could show that all. I should put different markers in here. Here, and here are all the same. So now I can prove that the two triangles are equal because of SSS, side markers. And then if the triangles are equal, then these angles are equal. Then, but again, by 10.1, the central angles are equal, so it forces the arcs to be the same. So it's like going backwards. You're almost doing the exact same proof, you're just going backwards through it, which I think is kind of interesting. That's how biconditionals usually work. Questions at all about the first theorem? So this is the start. It's showing that for some reason, chords are way more important than people think they are. So it's that starting part of it. Okay. All right, let's get rid of all this. Let's do our next theorem today. Next theorem. I don't know if we'll get to another one. This might be our only one today. So 10.3, I'll let you write it down. We'll talk about it. If a diameter or radius, it doesn't really matter if it's a diameter or radius because you can take half or a little piece of it, of a circle is perpendicular to a chord at any point. So you can put a chord anywhere you want. You put the radius or diameter, whatever you're looking at, perpendicular to it. What we need to prove that it bisects the chord, so it cuts the chord in perfect pieces. And here's the crazy part, and this is the part that's actually the most difficult. And the arcs are also the same. So that's like an extra step. So if we can put a radius or a diameter perpendicular to a chord, it will bisect the chord. It'll cut the chord perfectly in half. And then we got to prove that it will cut the arc in half as well. That's what the word bisecting means. This is probably going to be our last theorem of the day, just because I know the difficulty of this one. I'll let you write down. We'll go through it. Page in the book, I think it's 716, pretty sure. Let's see. It's 716, yeah. So, some people like to note that.
Do these have weird names or no?
What? No names for any of these, which is kind of weird. Because they're all just about arcs and chords, so that's just how I remember. Okay, questions at all before I give you the picture? Okay, so let me just show you a picture. That'll give you kind of a hint of what we're trying to show here. Okay, that's the idea. So we have a diameter or a radius. It doesn't really matter because we're really not even using this side over here, which I think is kind of funny. So like this part doesn't even matter. But anyway, we're taking your radius and we're going to put it perpendicular to a chord. So if you had the chord XY here, that's a chord cutting through the circle, hitting it, with the endpoints on the circle. And I put a radius so it's perfectly perpendicular to it. Prove that the sticks here are the same length. So we have to prove that ZY is the same exact length as a chord, or as this piece, is the same exact length as XZ. So I gotta prove like that's perfectly a midpoint. And then once I can get there, and I've done that, then I have to show, and this is the second part which is kind of difficult, then I have to show that the arcs are the same. Show that this arc is equal to that arc. So that's a secondary piece on this one. Alright, but we're going to do, say it again?
The measure of or the length?
The length of it, which would also in turn prove that the measures would be the same. Yeah, so it's kind of weird how these work on this. No, the actual steps, I don't think they're actually shown. No, okay. Alright, so let's walk through the actual proof. Let's go through the steps. The first step that I would do if I was ever doing this, so line number one, you have that this angle here are 90. And it doesn't matter what side you put, you can put the 90 anywhere you want because they're vertical, or the fact that these have to add it to be 180 because it is a straight line. So you can put the 90 degrees anywhere you want. So that would be like the line number one. We do have the radius being perfectly perpendicular to Z, or I guess XY. Second thing, I would draw in my radius, or radii, plural. What do we know about the radii of an actual circle? If I draw two of them, what can you tell me about those two radii? Yeah, they're equal in length. So this stick, CX, is the same as CY, because it doesn't matter where you put a radius. They're the same length. It's a hand on the clock. You can spin it anywhere you want. Radius is the most important number, the important stick in a circle. It's the thing that we use to find pretty much everything. All right. Now this one is kind of tricky, and I'm gonna click to the next part here, which is these are pretty much the only pieces I need, except for one more piece, to prove that the two triangles that I have here, I can prove that these two triangles are equal by using these pieces. Here's the reason why. If we go back to the little acronym system, one of these, very specifically, is used for right triangles. Anyone know which one is used for right triangles? I said it earlier. Which one specifically is used for right triangles? Bottom one, HL here. This is called the hypotenuse leg. So if I had a hypotenuse of a right triangle and I had a leg of a right triangle and those are matching on two different pictures, then the two triangles are equal. That's what the hypotenuse leg theorem says. Well, that's actually what we have here. You have a hypotenuse. This is the actual hypotenuse of that right triangle. This is the hypotenuse of that right triangle. They also share the wall in the middle right here. Now what is that wall in the middle of them called? Starts with an R. Say again? Reflexive, yeah, the reflexive wall. And this is just a leg. It's not a hypotenuse, so it's a leg of a right triangle. Well, if I have the hypotenuse and leg of one right triangle is equal to the hypotenuse and leg of another right triangle, then the triangles are equal. So this is actually the reason why. It's the number one reason why this thing works. And so now the fact that I can actually prove that the two triangles are equal because of this whole idea of hypotenuse and legs, then I can prove that these two sticks have to be the same. That would be the first part, because those pieces XZ and ZY are equal because of the corresponding parts. The triangles are equal, so those pieces have to be equal. They're visually matching. Third part. So I proved this. Prove that the chord was bisected. Prove that the two pieces are the same. We just did that. We proved that triangles are equal and those pieces have to be the same. Now, prove that the arcs are the same. Well, to get the arcs being the same, I basically have to get to this angle and this angle being equal. And they are. Those are corresponding pieces. That these central angles, that is a central angle, it's in the middle of the circle pointing outwards, that angle is equal to this one. So the central angles here are equal. They're corresponding pieces, CP, CT, C. Well, if the central angles are equal, the arcs are equal. That was theorem 10.1. That was the theorem we talked about earlier this week, and I used it in the previous one. The angles are the same, the arcs are the same. And that's the arc you're looking at. So this arc is actually perfectly split in half. The arc was actually bisected because those two arcs are the same. Because I'm using a radius and I have the same angle in the middle of the circle pointing at two different arcs. So it's if we were to write like every step of this theorem, I think it's like a 11-step proof. Because you have to prove the first part, which takes like 4 or 5 steps. Then you have to get to the next part, which you have to put all those pieces together. And I think in total, it's like 11 steps. And why it's 11? A lot of people are like, why isn't it just 6 or 7? Because you're not just trying to prove that the sticks are equal. You're actually trying to prove that they're bisected. So showing that they're equal gets you to the next step, which says, this, Z is the middle, B is the middle, and that they're perfectly bisected. All right, questions, comments about our theorems today? We're gonna stop there. I think that's pretty good. That's a good ending. All right, tomorrow we'll do a couple more. We have a couple more properties I want to cover tomorrow. We'll do a bunch of examples of like what homework will eventually look like for this. I don't think we're gonna get homework on this tomorrow because we got to do a bunch of examples. So probably next week. If you haven't read the announcements, I think I sent out an email this morning to the sophomores and junior classes. We're looking for student body president for next year for elections. I think the only requirement to run for student body pres, because that's the first thing we always have. GPA is one of them. I think that was in the email. And second, you had to be a member of the student council before, at some point in high school. So if you're a sophomore and you've been on the student council member, you're technically eligible as long as your GPA is good enough. So, but there you go. I think that was the email I sent out. I think elections are next week, but the applications are in the office if you want to run. And it's kind of the most important piece. So keep that in mind. There's a lot of responsibility for student council, or student body press. So, and they speak at graduation, I think, too. So, pretty sure. All right, questions? Perfect. All right. Now we're done for the day. Okay.